Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to continue our lecture on mathematics, and we've made it to the third objective, which is titled Trigonometry. Trigonometry is the study of relationships between the angles and the sides of triangles, specifically right triangles. In a right triangle, one angle is always 90 degrees. Now, the hypotenuse is the longest side of the triangle, and it's directly opposite the 90-degree angle. So in our triangle here, side C is the hypotenuse. The opposite side is the side opposite the angle you're focusing on, which we call theta. So this is our angle of interest, which means that the opposite side in this triangle is side A. The adjacent side is the side next to the angle theta, excluding the hypotenuse. So in this triangle, side B is the adjacent side. Now, trigonometric functions, they define the relationships between these sides. And the three primary functions are sine, cosine, and tangent. These are often remembered using the mnemonic SOHCAHTOA. Now, what do each of these parts stand for? Let's start with SO. This tells us that sine theta is equal to opposite divided by hypotenuse. So in our triangle, sine theta is going to be side A, which is the opposite side, divided by side C, which is our hypotenuse. What about CA? This stands for cosine theta is equal to adjacent divided by hypotenuse. So in our triangle, cosine theta is equal to side B divided by side C. Then TOA stands for tangent theta is equal to opposite divided by adjacent. So in our triangle, the opposite side is side A, and this is going to be divided by the adjacent side, which is side B. In addition to these functions, I want to note that each one has an inverse function. However, you're not going to be expected to do these calculations without a calculator. Instead, inverse trig functions are most likely to appear in questions asking for the direction of a resultant vector in vector addition or subtraction. With that being said, what is important to know is the values for sine, cosine, and tangent at specific angles: 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. These are commonly used in problems, so let's work through this table. At 0 degrees, sine is equal to 0 because the opposite side has no length. Cosine is equal to 1 since the hypotenuse equals the adjacent side, and tangent is equal to 0 since the opposite side is 0. At 30 degrees, sine is equal to 1/2, cosine is equal to square root of 3 divided by 2, and tangent is equal to square root of 3 divided by 3. At 45 degrees, both sine and cosine are equal to the square root of 2 divided by 2, and tangent is 1 because the opposite and adjacent sides are equal. At 60 degrees, sine is equal to the square root of 3 divided by 2, cosine is equal to 1/2, and tangent is equal to the square root of 3. At 90 degrees, sine is equal to 1 since the hypotenuse equals the opposite side. Cosine is equal to 0 since the adjacent side is 0. And tangent is undefined because the division by 0 is not possible. Now let's discuss the two special right triangles that make these values easy to derive. The first thing we want to talk about is the 30, 60, 90 triangle. The 30, 60, 90 degree triangle is a special right triangle that is derived by splitting an equilateral triangle down the middle. An equilateral triangle is a triangle where all of the angles are 60 degrees and all of the sides are equal. When we split an equilateral triangle down the middle, we're going to have one angle that's 30 degrees, one angle that's 60 degrees, and one angle that's 90 degrees. Now the sides of this triangle, they follow a fixed ratio of 1 to square root of 3 to 2. The shortest side, opposite to the 30-degree angle, has a length of 1. The longer leg opposite the 60-degree angle has a length of square root of 3. And the hypotenuse, which was originally a side of the equilateral triangle, has a length of 2. Now, using this triangle, we can actually determine the sine, cosine, and tangent of 30 degrees and 60 degrees easily. So for example, for 30 degrees, if that is our angle of interest, I'm going to circle it in red. Let's work through sine. Sine is the opposite side, which is 1, divided by the hypotenuse, which is 2. So sine 30 degrees is equal to 1 over 2. Cosine 30 degrees, this is going to be the adjacent side, which is square root of 3, divided by the hypotenuse, which is 2. So cosine 30 degrees is equal to the square root of 3 divided by 2. Tangent 30 degrees is going to be opposite side divided by the adjacent side. So here that's going to be 1 over square root of 3. You can alternatively write this as square root of 3 divided by 3 if you multiply both the numerator and the denominator by the square root of 3. What about for 60 degrees? So if 60 degrees is our angle of focus, I'm going to circle it in purple. Let's figure out sine, cosine, and tangent. Sine 60 degrees, this is going to be the opposite side, which is going to be square root of 3 divided by the hypotenuse, which is 2. So sine 60 degrees is square root of 3 divided by 2. Cosine 60 degrees, this is going to be the adjacent side, which is 1, divided by the hypotenuse, which is 2. So cosine 60 is equal to 1 over 2. Tangent 60 is going to be the opposite side divided by the adjacent side. So this is equal to square root of 3. Now that we've covered the 30, 60, 90 degree triangle, let's talk about the 45, 45, 90 degree triangle. This triangle is a lot more simple. It's formed by cutting a square diagonally in half, and that results in a right triangle with two equal angles of 45 degrees. The sides of this triangle are always in a ratio of 1 to 1 to square root of 2. The legs, as you see, are equal in length. They both equal 1 since they come from the square's side. And the hypotenuse is the diagonal of the square, and it has a length of square root of 2. Now, if we're trying to figure out sine, cosine, and tangent of 45 degrees, this is how we're going to work through this. Let's say that this 45-degree angle is our angle of interest. You can do it with either angle. They're both 45 degrees. You're going to get the same results. Sine of 45 degrees, this is going to be equal to the opposite side, which is 1, divided by the hypotenuse. This gives us 1 over square root of 2, which we can alternatively write as square root of 2 divided by 2 if we multiply both the numerator and the denominator by the square root of 2. Cosine 45 degrees, this is going to be equal to the adjacent side, which is 1, divided by the hypotenuse. So 1 over the square root of 2, which again, we can alternatively write as square root of 2 divided by 2. Tangent 45 degrees, this is equal to the opposite side divided by the adjacent side. So 1 divided by 1, and that gets us 1. So now we understand how we can use these two triangles, this 30, 60, 90 degree triangle, and the 45-45-90 triangle to derive this table. So if you don't want to memorize this table for the MCAT, just know how to figure this out from the triangles themselves. With that, we've completed objective 3, and now we can move into our last and final objective, which is titled problem solving. To start, it's important to understand the concept of direct and inverse relationships between variables. In a direct relationship, as one variable increases, the other increases proportionally. So for example, in the formula F equals ma, force is directly proportional to mass if acceleration is held constant. That means that doubling the mass doubles the force. On the other hand, in an inverse relationship, as one variable increases, the other decreases proportionally. So a common example is the relationship between pressure and volume in Boyle's law. An increase in pressure causes a decrease in volume if temperature is held constant. Next, solving problems often requires unit conversions. To convert between units, we have to be familiar with the metric prefix scale. This provides a systematic way to represent and work with very large or very small numbers. So let's go over some of the most common metric prefixes we're going to see on the MCAT. Let's start with mega. Mega represents 10 to the 6, or 1 million times the base unit. So for example, 1 megawatt is equal to 1 million watts. What about kilo? Kilo corresponds to 10 to the 3, or 1,000 times the base unit. So 1 kilogram is equal to 1,000 grams. Deci is another really common one. So that is equal to 10 to the minus 1, or 1/10 of the base unit. So for example, 1 deciliter is equal to 0.1 liters. Centi represents 10 to the minus 2, or 1/100th of the base unit. So 1 centimeter is equal to 0.01 meter. Milli stands for 10 to the minus 3, or 1,000th of the base unit. 1 milligram is equal to 0.001 grams. Micro corresponds to 10 to the minus 6, or 1/1,000,000th of the base unit. So 1 micrometer is equal to 0.000001 meters. And then finally, nano represents 10 to the minus 9, or 1/1,000,000th of the base unit. So 1 nanometer is equal to 0.000000001 meter. I know that was annoying, but that's okay. So these are some very important metric prefixes that we should be familiar with. Along with metric prefixes, it's also important to know common conversion factors that appear frequently on the MCAT. We should know that 1 mile is equal to 5,280 feet. We should know that 1 foot is equal to 12 inches, and 1 inch is equal to 2.54 centimeters. In addition, 1 calorie, this is written with a capital C and used for food energy, that's equal to 1,000 calories. So this distinction is really important in nutrition because the capital calorie represents the energy content of food. 1 calorie, lowercase c, this equals 4.184 joules. This conversion is really important in thermodynamics and chemistry, where energy is often measured in joules. 1 electron volt is equal to 1.602 times 10 to the minus 19 joules. This is commonly used in physics to describe the energy of particles or photons. We also need to know that 1 liter is equal to 33.8 ounces. 1 pound is equal to 4.45 newtons. And 1 atomic mass unit is equal to 1.661 times 10 to the minus 27 kilograms. Let's go ahead and tackle a practice problem. This problem says a car speedometer registers a speed of 33 miles per hour. What was its speed in meters per second? We know that our speed is 33 miles per hour. Our ultimate goal is to re-express this in units of meter per second. Let's start by focusing on converting miles to meters. We know that 1 mile has 5,280 feet. This way we can get rid of our miles unit and we're left with feet. We know that 1 foot is equal to 12 inches. So now we can cancel out feet and we're left with units of inches. 1 inch is equal to 2.54 centimeter. Inches cancel out, we're left with centimeters. And now we can use our metric prefixes to convert from centimeters to meters. 1 meter is equal to 100 centimeters. So we get to cancel out our units of centimeter and we're left with units of meter. When we carry out this calculation, we get 53,108 meters per hour. Now that we have miles converted to meters, we can focus on converting hour to seconds. So we know we have 53,108 meters per hour. So let's apply all the necessary conversions to go from hour to seconds. We know that in 1 hour, there is 3,600 seconds. So this way we get rid of our hour unit, and we're going to be left with units of seconds. When we carry out this calculation, we get 14.8 meters per second. So 33 miles per hour is equivalent to 14.8 meters per second. And with that, we have solved this problem. Let's move on to our next topic. That topic is temperature conversion. Temperature often needs to be converted between different scales, especially between Fahrenheit, Celsius, and Kelvin. These two equations help us interconvert between different scales. This first equation shows us how to convert Celsius to Fahrenheit. Fahrenheit is equal to 9/5 multiplied by Celsius plus 32. This second equation shows us how to convert Celsius to Kelvin. Kelvin is equal to Celsius plus 273. Now that we've covered temperature formulas, metric prefixes, and common conversions, we can put a name to the method that ties all of these topics together. And that method is dimensional analysis, also known as unit analysis. Dimensional analysis is a systematic approach that allows us to solve problems by focusing on the relationships between units. It's a tool that not only ensures our calculations are correct, but it also provides a clear framework for breaking down complex problems into manageable steps. In dimensional analysis, units are treated like algebraic variables that can be multiplied, divided, or canceled out. This means that every step in our calculation is guided by the units, and that helps us verify that the answer makes sense and is expressed in the desired form. For instance, in the last problem we solved, we applied this method directly by systematically converting between units and using the relationships we've just discussed to go from miles per hour to meters per second. And by naming and formalizing this process, we gain a deeper understanding of how metric prefixes, conversions, and formulas work together in problem solving. With that being said, let's jump into a practice problem. This problem says the ejection fraction is the proportion of the blood volume in the left ventricle expelled with each contraction of the heart. A patient is known to have an ejection fraction of 0.6, a cardiac output of 5 liters per minute, and a heart rate of 80 beats per minute. What is the volume of blood in this person's left ventricle just prior to contraction? Let's break this down. The ejection fraction is the proportion of the blood volume in the left ventricle that's expelled with each heartbeat. We're told that the patient has an ejection fraction of 0.6. This means that 60% of the blood in the ventricle is ejected during one contraction of the heart. Now, to determine the total volume in the ventricle before contraction, we need to follow a couple of steps. In the first step, we want to calculate the volume of blood ejected per heartbeat. We're given that the cardiac output is 5 liters per minute, and we're also given that the heart rate is 80 beats per minute. To find the blood ejected per beat, we're just going to divide the cardiac output by the heart rate. So the volume per beat is equal to 5 liters per minute divided by 80 beats per minute. Notice that the units minute cancel out. We're going to get our final answer in units of liter per beats. And if we calculate this, we get 0.0625. So the heart ejects 0.0625 liters of blood with each beat. Now, in the second step, we want to relate the ejected volume to the ejection fraction. So the problem states that 60% or 0.6 of the total ventricular volume is ejected during each beat. This means that 0.0625 liters represents 60% of the total volume. So mathematically, we can express that in the following way. 0.0625 is equal to 0.6 multiplied by the ventricular volume, which I'm going to write as VV. Now we can move into our last and final step where we can solve for the ventricular volume. All we have to do is divide both sides by 0.6. When we do that, we get 0.104 liters. So the ventricular volume is equal to 0.104 liters. The volume of blood. Let me reiterate. The volume of blood in the left ventricle just before contraction is equal to 0.104 liters. And with that, we've solved this problem, and we can move into our last topic, which is algebraic systems. Algebraic systems refer to situations where you are solving for multiple variables that satisfy two or more equations simultaneously. The goal is to find the values of these variables that make all of the equations true. There are 3 common methods for solving algebraic systems. They are substitution, elimination, and setting equations equal to each other. In substitution, this method involves isolating one variable in one of the equations and then substituting its expression into the other equation or equations. In elimination, you manipulate the equations by adding or subtracting them to eliminate one of the variables. This is often achieved by first multiplying one or both equations so that the coefficients of a variable are the same or opposites. In the final method, we set equations equal to each other, and this method is useful when both equations are already solved for the same variable. Now let's go ahead and solve this problem here using each of these three techniques. Our first equation that we have is 5x minus 2y is equal to 11. The second equation we have is 3x plus 4y is equal to 17. Now that we have two equations and two unknown variables, we can solve for both variables using one of our three methods. Let's start with substitution. In substitution, we want to solve for one variable in one of the equations and then insert this term into the other equation. So let's take advantage of this first equation and let's solve for y. In order to do that, we're going to subtract 5x from both sides, and then we're going to divide both sides by minus 2. When we do that, we get that y is equal to 5x minus 11 divided by 2. Then we're going to take this equation for y, and we're going to plug it into the second equation. So we have 3x plus 4y, where y is equal to 5x minus 11 divided by 2, and that is all equal to 17. Now here we can do a little bit of simplification. We can divide this by 2 and this by 2. This becomes 1 and this becomes 2. So now we have 3x plus 2 multiplied by 5x minus 11, and that's equal to 17. Let's distribute this 2. When we do that, we get 3x plus 10x minus 22 is equal to 17. Let's add these terms together. 3x plus 10x is 13x. And then let's add 22 to both sides. So now we have 13x is equal to 39. Then if we divide both sides by 13, we get that x is equal to 3. Now that we know what x is, we can solve for y. We can go ahead and plug 3 into our expression for y. So we have 5 times 3 minus 11 divided by 2. This is 15 minus 11, which is 4. 4 divided by 2 is 2. So y is equal to 2 and x is equal to 3. So this is how we use substitution to solve for our two variables using the two equations we're given. Let's try another technique. Let's try setting equations equal. I went ahead and erased the board, and now we're going to try a different method. Setting equations equal to one another is a specialized case of substitution. In this method, we solve for the same variable in both equations and then set the two equations equal to each other. So let's solve both equations for y. We already did it for this first one when we did substitution. We said that y is equal to 5x minus 11 divided by 2. Let's do it for this second equation as well. What I'm going to do here is I'm going to subtract 3x from both sides, and then I'm going to divide both sides by 4. So we get that y is equal to 17 minus 3x divided by 4. Now we can set these two things equal to each other because they both equal y. So we get that 5x minus 11 divided by 2 is equal to 17 minus 3x divided by 4. Now I'm going to cross multiply here, and that gets us 4 multiplied by 5x minus 11 is equal to 2 multiplied by 17 minus 3x. I'm going to divide both sides by 2. So this gets us that 2 multiplied by 5x minus 11 is equal to 17 minus 3x. Let's distribute this 2. This gets us 10x minus 22 is equal to 17 minus 3x. Now I'm going to add 3x to both sides so we can get rid of this term on the right. And then I'm going to add 22 to both sides so I can get rid of this term on the left. This leaves us with 13x is equal to 39. And if we go ahead and divide both sides by 13, we get that x is equal to 3. Now, if we take x is equal to 3 and go ahead and plug it back into one of these expressions for y, we get 5 times 3 minus 11 divided by 2. So this is 15 minus 11, which is 4. 4 divided by 2 is equal to 2. So once again, we get the same answer. X is equal to 3 and y is equal to 2. So now we've done 2 methods and we get the same answer. Let's go ahead and try our third and final method, which is elimination. I'm going to go ahead and erase the board and we'll get started. In elimination, you want to multiply or divide one or both of the equations to get the same coefficient in front of one of the variables in both equations. Then you can add or subtract the equations as necessary to eliminate one of those variables. So here I'm going to keep 3x plus 4y is equal to 17 as is, and then I'm going to multiply this equation by 2. That gets us 10x minus 4y is equal to 22. Now, when we add both of these equations together, we get 13x. The plus 4y minus 4y cancel out, and that is equal to 17 plus 22. That's 39. So what we're left with is that 13x is equal to 39. Let's divide both sides by 13. That gets us that x is equal to 3. Now we can take this and plug it into either one of our equations to solve for y. So let's do our first equation, 5x, x is 3, minus 2y is equal to 11. This is 15 minus 2y is equal to 11. I'm going to subtract 15 from both sides, and now I have minus 2y is equal to negative 4. I'm going to divide both sides by negative 2 to get that y is equal to 2. So once again, notice we get the same answer. X is equal to 3, y is equal to 2. So you can use any one of these 3 methods to solve algebraic systems. They will get you the same answer. It's really a matter of preference. And with that, we've covered everything we want in this chapter. I hope that it was helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.